Here we go. So we are going to go over the examples that we worked on yesterday and discuss them. So these are, by the way, similar to the problems that I put on exercise set 7. Like they're the same type of problems, which is to say you have a series and you're just trying to figure out if it converges or not. And you've got all these tools. You've got all these different tests you can do. Now, I will say I'm not going to bother going into the actual partial sums and like looking at the sequence of partial sums for any of these. Today, I want to focus on applying the convergence tests for these things. So let's start with number 1. It's always good to do the divergence test. Does 1 over n factorial go to 0? As a sequence? What do you think? Hang on, I should write down the let's write down what it is so we can zoom in on it. It's the 1 over n factorial. Okay, a divergence test. Yes, the sequence definitely approaches 0. How can you tell? I mean, the numerator is 1 and the denominator is getting bigger and approaching infinity. So therefore, 1 divided by bigger and bigger and bigger things is going to be closer and closer to 0. Yes. So, okay, that means check. It passes that divergence test. I'll put it over here because I don't want to take up too much space. Yep. Okay, so let's try a different test. Integral test? How about nope? I never taught you guys how to integrate n factorial or 1 over n factorial. So n factorial is not integrable in this class. If you're interested in how you can integrate, if you're interested in how to extend the idea of factorial to real numbers instead of just integers, look up, I think it's called gamma functions. Not gamma particles, not somebody mentioned was it the Hulk? I think a gamma function. Yeah, a gamma function is sort of like the extension of the concept of factorial to. So anyway, we're not going to do integral tests. So basically that kind of leaves us with just like comparison test at this point. Okay. How could we compare this? So 1 over n factorial. We want to ask if that's greater or maybe less. I did those backwards. Greater or less than something else. So what should we compare to? If you compare to like 1 over n, for example, then let's see. This should be less, right? Because with a larger denominator, we're talking, n factorial is going to be larger, greater than or equal to n. So we have this relationship. Okay. But the 1 over n harmonic series diverges. So if we're looking at a smaller sequence and the one we're comparing to diverges, that's no conclusion. So that comparison doesn't work. But there's other comparisons we can do. What if you compare to 1 over n squared? Okay. Well, if you compare n squared versus n, which one of those is bigger or smaller? I'm sorry, n factorial and n squared is what I meant to say. Well, 1 factorial is 1 and 1 squared is 1. 2 factorial is 2 and 2 squared is 4. So far it's looking like the squaring function might be bigger. 3 factorial is 6 and 3 squared is 9. But then 4 factorial is 24 and 4 squared is 16. 5 factorial is, what is that? 120. 5 squared is 25. And despite the fact that in the first few cases the squaring function was bigger, it soon becomes very obvious that as n grows, what is this, 720 or something? 6 squared is 36. The factorial function is growing way bigger, way faster than the squaring function, right? So that would mean the relationship is this direction, at least for n greater than or equal to 4. Okay, that inequality is not true for the small n values up here. For the small n values 1, 2, and 3, it's the other way around. But we don't really care because the comparison test, all that really matters is what happens on the at the end, what happens in the long run. So we can just say, all right, well, for n values after a certain point, this inequality holds. And then we can say, well, since the 1 over n squared series converges, so must the 1 over n factorial series. So the answer is converges. Okay. So there's number 1. Let's look at number 2. Number 2 is pretty quick. Number 2 here is summing up natural log of n over n. Passes the divergence test. Integral test is a nice one here. Okay, so you can do integral of ln n over n, 1 to infinity dn. We actually should really do it dx. I mean, it's okay to write it with n's, but technically you should do this with x's because n is an integer variable, whereas x is a real variable. And in order to integrate, you've got to be talking about a real function, not an integer only function. So whatever, it doesn't really matter, but I thought I'd make that point. U equals natural log of x works great here because du is the 1 over x dx. So what we have here is 0 to infinity u du. And then we have 1/2 u squared from 0 to infinity. And this clearly is infinite. So the answer is that the series diverges. Is that right? Yeah. Diverges by the integral test. All right. So now you guys struggled on number 1, but comparison, the concept of the comparison test is pretty new and factorials are not very familiar. But I hope that now that you see the concept, see how we can do the comparison test on number 1, you can see that that's fairly simple. Number 2 is fairly simple due to that integral test. But number 3 gave you guys a lot of trouble, and rightly so. How could we possibly go about figuring out number 3? Integral test is off the table again. It's got that factorial in the numerator. Divergence test? Tell me. Okay, so if we try to apply our initial divergence test, just what's going on with the sequence? What is the limit as n goes to infinity of n factorial over 3 to the n? What is that limit? Equals what? Do we have a guess at least, even if we don't know? I mean, it's infinity over infinity in form, right? So it is an indeterminate form. Daniel points that out, which is good. Usually what we would want to do, or what we might want to do, is apply L'Hopital's rule. But with a factorial function, again, we don't have integrals or derivatives of a factorial function because we We don't really have a concept of how that could be applied, how that could be defined on real numbers. We only understand it as a function on integers. So that takes L'Hopital's rule off the table, right? So we have 0 infinity over infinity, but L'Hopital cannot be applied to the factorial function. So yeah, some sort of comparison, Cheyenne suggests. Yeah, that's a good idea. What could we compare this to? Isa suggests n factorial over n. If you compare to n factorial over n, we would still then need to know what that limit is. Do you know any better what that limit is? Oh, well, I guess, are you suggesting, Isa, are you suggesting like a limit comparison? Because if you're, so Isa is suggesting that we compare it to something with an n factorial so that it sort of cancels out. The n factorial would cancel out. If you were going to cancel it, it would mean that you would be looking at a ratio of two things, right? So, yes, limit comparison test might work. That's true, but I want to walk back from the limit comparison test because we're still trying to perform the divergence test right now. So when so I know Cheyenne said comparison test, but actually I want to stick with the divergence test. I just want to talk about the limit of this sequence for the moment. Because this does actually equal infinity, and you can show that it equals infinity. Let's examine n factorial. N factorial is n times, so this is going to be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times ... all the way up to times n, wherever n is. And as n grows, that'll, that multiplication will grow, right? So this is the product of all the numbers up to n. Let's compare this to something like 2 to the power n, which is 2 times 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 ... all the way up to 2. It has the same number of factors because from 1 to n, there's n of those. That is how many factors there are. This is n of them as well, n factors. It's just that here, the factors go from 1 up to n. Here, they are all equal to 2. Which of these is bigger? Here, we have 1 is less than 2. But here we have equal. And then after that, we have 3 is greater than 2. 4 is greater than 2. 5 is greater. 6 is greater. 7 is greater. 8 is greater. All the way down. N is going to be greater than 2. Right? So if we compare these factors, we can see that overall, at least for large values of n factorial should be greater than 2 to the n, right? Similarly, three to the n, you might have, you might say 1 is less than 3, 2 is less than 3, 3 is equal to 3, and then after that, we have 4 is greater than, 5 is greater than, 6 is greater than, 7 is greater than, right, and so on. So comparing the n factorial and the 3 to the n. So I'm kind of crossing out that one and ignoring it for the moment. Okay. Just look at the n factorial of 3 to the n, and the relationship is the same. N factorial is still greater than 3 to the n, right? N factorial is greater than 4 to the n, because there's what there will be is some small number of cases where it's less, where the factor is less until it's equal, and then after that it's greater. The n, these values are going to be bigger than these values. So this is sort of a rough argument, but it can sort of be extended. If you want to really learn about how to prove that n factorial is greater than like any exponential function, it will eventually surpass any exponential function, no matter what your exponential base is, no matter how large that base is, that growth factor. You can prove that. If you're more of a discrete math topic, I cover how to prove things like that. I think that this would be a good candidate for the application of proof by induction for my two of you who are in discrete math. But anyway, we're not going to prove that here. So we have n factorial is greater than any of these. So what I'm suggesting we do is look at like 3 to the n over 3 to the n. If I do that and if I compare my n factorial over 3 to the n to 3 to the n over 3 to the n, which one is bigger? That guy, right? Because the denominator is the same, but the numerator on this numerator is bigger than this numerator, right? So this equals 1, right? Adding up ones is definitely going to diverge, isn't it? Adding up n factorial over 3 to the n is going to diverge as well then. That's my comparison test. I actually realized that I chose the wrong number. What I should have chosen here, if I'm doing divergence test, what I should have chosen here is 4 to the power n. That's not equal to 1. We can view this as 4/3 to the power n. This diverges. It's geometric with r greater than 1. Okay. R equals 4/3, bigger than 1. And so therefore, the sequence n factorial over 3 to the n diverges by comparison to 4/3 to the n. Okay, that sequence diverges. So this is just the divergence test, remember? All we're doing is looking at the series and trying to figure out if the sequence we're adding up approaches 0 or not. It doesn't. It goes to infinity. This equals infinity. And so the series can't possibly converge. The sequence doesn't have the right behavior. Okay. So what I kind of presented here is just the idea of looking at the divergence test, just doing the divergence test on it, but you can also do comparison test to something like 4/3 to the n or 1. 3 to the n over 3 to the n is equal to 1. One of those things would work as well. Okay. Let's look at some of these. Let's look at some of these alternating series. So let's look at 4 here. -1 to the n times sine squared of 1 over n. How can we go about this? We just want to know, first of all, if it is convergent. Oh, I just want to comment. I just noticed another. So Isa, you had said something earlier that I don't think I noticed. N to the power n is something that we will study soon. We'll be looking at n to the power n in about 20 minutes, I think. when we do the ratio test. But n to the power n is, I believe, I can't remember if it grows faster or slower than n factorial. I think it's slower. No, faster. No, yeah, it's fat. Oh, sorry, it's definitely fat. It's definitely, it grows faster. N to the power n is bigger generally than n factorial. We'll get back to that. All right, yeah, looking at number 4 here. What do we do with this guy? We just want to apply our alternating series test, right? The AST. Really, we just want to look at the limit of this sequence, right? This is like applying the divergence test, except since it's an alternating series, we have the potential to get more information out of it, right? It's actually going to be conclusive this time. So what is this doing? Well, if you look at 1 over n, that's approaching 0. And what's sine squared of 0 equal to? Zero. Sine of 0 is 0, so if you square it, it's still 0. So since this was an alternating series, we can say that the series converges. Okay, the series converges because that approaches 0. So that's nice, right? If it hadn't been an alternating series, then this would have been harder to handle. Okay, if it hadn't been an alternating series, then I think that this would have been like inconclusive, right? Because we basically would have been talking about doing the divergence test, and getting 0 is an inconclusive answer, right? So the fact that it's alternating was very important there. So now we're gonna think about absolute convergence. If we take the absolute value here, we just are looking at this part alone. So here we took away the factor that makes it alternate. Now this is positive. It's note that it's positive because of the fact that it's squared. It's positive because it's squared. It's never actually equal to 0 because the sine function is only equal to 0 at multiples of pi, and 1 over n is never going to give you a multiple of pi. So you'll never actually get a 0 value. It's strictly positive. Okay. But what's going on with that? It is approaching 0. We know it's approaching 0. We already did that. So we know it passes the divergence test. That's shown above. So what could we do with it? Integral test? Can you integrate sine squared of 1 over n? You integrate sine squared of 1 over n? I want to share the funny comment that Ryan made yesterday, which is that my calculator can, which it probably can. Wolfram Alpha can too, but do we know how to do that? I don't think we do. I don't know how to do that. I'm kind of curious what it is. Integral of sine squared of 1 over x. Yeah, it uses some type of functions that we haven't learned about yet. This what's called the sine integral. Yeah, it's one of the Fresnel integrals actually. No, it involves one of these. Here, I'll show you. So integrating it is technically possible, but it sort of involves this thing here, which is one of these integrals that of a function that doesn't have a It doesn't have an antiderivative. I'm trying to remember that what I told you. There's a name for this. It's called a something integral. I forget. We talked about these when we were doing like approximation by Riemann sums, doing like midpoint and trapezoid rule and that kind of stuff. I forget what it's called. Anyway, so that's the sort of integral that you can really only approximate the value of. So you know, that's one approach. We could, but I don't want to take that approach right now. So we're not going to try integral test. Integral test is too hard. So that leaves us with comparison or limit comparison. Any ideas regarding comparison or limit comparison? Was anybody able to find something that works? Do we have anything? Anybody find anything yesterday? Compared to like a cosine squared of 1 over n or the absolute value of 1 over n? Well, do we know what those things are doing? Do we know whether those things converge or diverge? So the two suggestions are the absolute value of sine of 1 over n or the cosine squared of 1 over n. Do we know if those converge or diverge? Cosine squared of 1 over n definitely diverges by the divergence test because it approaches 1. So that's a fair point. But the comparison test is actually only valid if we have the original comparison test is only valid if we have I think they're both had to be decreasing, and sine squared is decreasing, but cosine squared is increasing. The sine squared of 1 over n I think looks like that, and cosine squared of 1 over n looks more like that. And so I think that makes it sort of an invalid thing to compare to. But limit comparison might be more effective. Yeah, let's consider limit comparison. What could we compare against? Like a 1 over n maybe, or 1 over n squared, one of those. I just want to so you don't have to take my word for it. I was going to show you what that looks like. That's generally decreasing after the initial wiggle. Cosine squared of 1 over x, though, is generally increasing after the initial wiggles. We have the decreasing and the increasing. So that makes cosine squared of 1 over n not a valid comparison. They have to be decreasing only. Okay. So let's try a limit comparison to something. Limit compare. Let's start with 1 over n. See if that works. Do 1 over n. So we're going to do the limit as n goes to infinity of our series, or the sequence that we are looking at, that we're examining, our sine squared of 1 over n, divided by 1 over n. And that is in the form 0 over 0. Okay, it is indeterminate 0 over 0. So we can apply L'Hopital's rule to that right away. What do we get? 2 times sine of 1 over n times cosine of 1 over n, and then times the derivative of 1 over n. Whatever that might be, the derivative with respect to n, I guess, which is negative 1 over n squared, I guess. We can write that out. Negative 1 over n squared. But that exact same thing is going to be in the denominator because it's the derivative of 1 over n. So that's going to cancel out. and we just have this by the chain rule here, 2 times sine of 1 over n times the cosine of 1 over n. What's that approaching? Do it here. Sine of 1 over n is approaching 0 because we have 1 over n, as n goes to infinity, 1 over n is going to go to 0. We got sine of 0 is 0. Cosine of 0 is 1. We've got 2 times 0 times 1. That's a 0. Okay. So, not ideal. Because we were comparing to a divergent series and we got 0 from this limit comparison. So that didn't work great. So that is a no conclusion result. So we could try something else. Let's try the same thing with 1 over n squared and see if that works any better. Again, we can start right away with L'Hopital's rule because it's 0 over 0. So we have the same thing in the numerator. Let's write that out again. Negative 1 over n squared. But now our denominator, the derivative of 1 over n squared, is negative 2 over n cubed. Okay. So we do have some canceling, but it's not quite as much canceling as it was before. So the negatives cancel, the n squared cancels here and brings us down to n to the first power. So what we have is that we have 2 over n down here. Oh, the 2's cancel out. I guess we can cancel the 2's. There we go. So this becomes just 1 over n in our denominator. So 1 over n down there. Okay. So now we have sine of 1 over n times cosine of 1 over n, all divided by 1 over n. This is still a 0 over 0. So we can do another L'Hopital's rule. Do a product rule in the numerator. We get cosine squared of 1 over n times negative 1 over n squared. And then plus sine times the derivative of cosine, which is actually a minus sine squared of 1 over n times negative 1 over n squared. And then all over negative 1 over n squared, the derivative of 1 over n. So like before, that cancels out from all 3 of those locations, right? You can factor it out of the numerator and cancel it with the denominator. We end up with this. We have cosine squared of 1 over n minus sine squared of 1 over n. And that, as n goes to infinity, is 1 minus 0, which is 1. That worked, okay? Do you remember what the conclusion is when you do the limit of the ratio and you get something like 1, which is not 0 and not infinity? It's either, yep, Isha's got it in the chat there. It's either they both converge or they both diverge, right? It's kind of like the integral test where they have the same result, right? They have the same convergence property. So since we were comparing to 1 over n squared, since that series converges, we can say that this series converges as well. So what that means about the original, going back to this guy, our original alternating series, is that this alternating series not only converges, it converges absolutely. Okay, it converges absolutely. Okay, I'm going to squeeze 5 into this little gap here because 5 is an easy one. 5 is pretty quick. 5, we had here the -1 to the n over square root of n. The AST, since 1 over the square root of n goes to 0, it converges. But the 1 over square root of n is a divergent series. Diverges because its p equals 1/2, which is less than 1. It's a p series, right? So that means that it converges conditionally. Okay, the alternating series converges conditionally. Okay, so I gave you these because one is an example of converging absolutely, and the other is an example of converging conditionally. Okay, I know we're going kind of fast, so let me pause. How are we doing? I'm hoping that since you guys worked on these yesterday and you've had a chance to look at them and think about them, that like now seeing ways that you can solve them is a little bit more approachable, right? I know that this was pretty messy. Get down here, having to do that L'Hopital's rule twice. We had to use like the chain rule, and we had to use the product rule and all that stuff. So it's definitely like, oh man, all that Calc1 is coming back to haunt you, right? It's like it's all still here. We still have to use it. I can understand that can be a little bit tiring, but I don't know. Besides getting into the weeds with L'Hopital out down here, I hope the concept works out okay, and you can see like, aha, yes, I see how, comparing to 1 over n was a no conclusion, but comparing to 1 over n squared gave us that they have the same convergence, and that kind of allows us to make this conclusion about this other series, and the reasoning all I hope makes sense, even if the details are a bit complicated. All right, so I want to look at this last one, number 6, cosine of n over e to the n. This is maybe the hardest one I gave you. It's not really an alternating series, because cosine of n, although cosine of n fluctuates between positive values and negative values, they're not necessarily alternating. Because if it was like, well, because pi over 2 is like 1.5 units apart. So every now and then you're going to have 2 in a row that are either both positive or both negative. So look at that and do that. Oh yeah, no, it's more than that. It's every pi units, which is 3 apart. So like, yeah, certainly you're going to have like repeats like that. And you've got like 3 negatives and then 3 positives and then 3 negatives and then, or maybe, yeah, and then 1, 2, 3, 4 positives and then sort of, it's fluctuating, but not directly alternating. All right, so we can't use the alternating series test. So what can we use? Because pretty much all the other tests require a positive series. Even the comparison test requires a positive series. Comparison to 1 over e to the n is a great idea, except that this is not a positive series. So we can't immediately compare to 1 over e to the n. But what could we do first before we make that comparison? Yes. Look at the absolute value. if we do the absolute value of cosine of n over e to the n, now we are talking about a strictly positive series, and we should be able to compare. So this gives us, hey, if we take that cosine of n, whatever that is, it's going to be less than 1. Okay, definitely less than 1. If I divide both of these sides by e to the n, I still have the same inequality. That's valid. Okay, so the sequence terms are less than those of 1 over e to the n. What does 1 over e to the n do as a series? Converge or diverge? How do we know that one converges? Let's just review that. How do we know this converges? But why does it converge? It might be useful to look at it as 1 is the same as 1 to the n. If you take 1 to the power of something, it's always equal to 1, right? So like 1 to the n and 1 are both equal. So this is 1 over e power n. It's not a p series. It's a geometric series. Yeah, and 1 over e, 1 over e is about, well, it's 1 divided by 2.7 something. So whatever it is, it's less than 1, right? Because we're splitting 1 into 2.5, 2 and a bit, 2.7-ish pieces. That's smaller than 1. So it's a geometric series with a rate of growth less than 1, which means that it is going to converge to, the series will converge. There we go. Series converges. So by comparison, this series converges. And so this original series is absolutely convergent because its absolute value series converges. What does that mean about its convergence? Does this series converge as well? Yeah, when I first introduced this idea of absolute convergence, one of the theorems about that was that if the absolute value of the series converges, the original series converges as well. It has to. So it's also regular convergent. Okay, so there we go. It's convergent and it's absolutely convergent. So, or it's convergent, I guess, because it's absolutely convergent. Yeah, that sort of thing. You might have been able to do that one by the integral test, by the way. Did anybody try integrating cosine of x over e to the x? I think you might be able to do that by parts. But I think this strategy is much simpler. So I was planning on going over this stuff with you guys and then starting the next section, but it's like 12:45. So I think we're actually going to stop. We're just going to stop. I don't think we need to do the rest. I think this took a little longer than I was expecting. Should have known this would take a long time. It was a lot of examples. But we've got another class tomorrow. So we'll do the ratio test and the root test then. Have a great day, folks. Every time I touch my mouse, it just scrolls away.